Hello, my deep thought thirsting viewers, and welcome to this week's episode in Physiology in Focus. This week's episode is going to be called Actin Up, where we will guide you through a crash course on actin, its role in the body, and its formation.
Yes, let's jump right in. Actin is a protein that's found mostly in your muscle cells, along with its buddy protein, myosin. Myosin has on the ends, they're called heads, and they pull on the more structurally sound actin filaments.
This, in what turn, is what allows for that famous muscle contraction and allows you to get those sick gains at the gym. BJuice.com has a wonderful article on actin-myosin interactions and the sliding filament theory as a whole.
Right, but there's actually more than one type of actin.
Inside you, there are two forms of actin, F-actin and G-actin.
So the G in G-actin stands for globular, and the F stands for filamentous.
The G-actin forms in groups of four called tetramers.
And these tetramers then make long chains or filaments called F-actin.
Yeah, Jamie, pull up that actin forming animation.
So the interesting thing that we can see here is that the G-actin gets added on as a continuous chain.
Oh, really?
Yeah, so the actin filaments have what's called a plus end and a minus end.
Is that related to the charge of the molecule?
Well, that's what I thought at first, but that's actually not the case.
Then what is it?
So the plus end is where the G-actin gets added on to the F-actin, and the minus end is where it falls off.
What do you mean it falls off?
So it kind of falls off. The G-actin gets its energy from this molecule called ATP, and that allows it to be added onto the chain. When it releases the energy and reaches the other end of the chain, it then falls off.
So I heard that actin fibers assemble and disassemble at the same rate. Is that true?
Yeah, and it's in a process called treadmilling. The actin keeps the same length, but it can kind of move because it's being built in a certain direction. This is excellently described in the textbook, The Cell, A Molecular Approach.
So if actin is continuously breaking and being rebuilt, then how do you get any actual use out of your muscles?
So there's an important distinction that we have to make here, and that's that the structures around the actin itself in your body cells are a little different than they are in muscle cells.
Oh, wait, I do think I remember reading about that. The actin in your cells is packaged up a little differently how it is in muscles, correct?
Yeah, so the actin in your cells is usually used to move the cell's membrane and thus the cell. These filaments typically are free-floating so that they can be used quickly to make changes in the membrane. The actin filaments in your muscle cells, however, are surrounded by other proteins that lock them in place.
Oh, okay. So the actin filaments are surrounded by three different proteins: tropomodulin on the minus end, Cap Z on the plus end, and tropomyosin on the sides. This in turn creates very stable filaments, which will help in resisting the force of contraction.
Some of these proteins change how fast the filament assembles and disassembles, right?
Right. Specifically, tropomodulin and Cap Z. Cap Z literally caps the plus end, preventing the filament from extending, and tropomodulin caps the minus end, preventing disassembly. David Gokin wrote an informative review on these proteins.
So what does the tropomyosin do then if it doesn't affect assembly or disassembly?
That one helps the fiber maintain stability. It comes in handy when resisting forces during muscle contractions.
Are these the only proteins that work on actin?
No, there's actually a whole slew of them. Profilin is a protein that binds to G-actin and promotes the addition of G-actin to the plus end, while disassembly stays the same at the minus end.
Oh, cool. And with profilin, we can form long polymers, overcoming the rate of disassembly by increasing the rate of assembly, effectively increasing the length.
The other major proteins that interact with actin have a lot to do with how actin is organized.
Is that where the term parallel bundles comes from?
Yes. F-actin can be organized into parallel bundles. This is usually done by proteins which are typically connected to the plasma membrane. These in turn encourage actin chains to form parallel branches. This is typically done in a cell to move the cell membrane and form filopodia, which are like little cellular arms.
And these parallel branches are less stable on their own, so they're connected and stabilized by a protein called facin.
Fascinating. But actin also forms into more tight networks too. These are facilitated by a protein called ARP23.
As detailed in a paper by Isabel Rauweiler, ARP23 is a cool protein which mimics the structure of G-actin and binds to the sides of F-actin to create new F-actin branches. This creates 2D F-actin networks with branches at 70-degree angles and 3D networks that are loosely linked at right angles.
There are also proteins called WASP-P, WAVE, and others that help regulate where ARP23 gets placed.
The ARP23 does this to ensure that at long lengths, the actin doesn't do crazy things if it reaches its persistence length.
So I've heard about persistence length, but what exactly is it, and what do you mean by crazy things?
So, first, let's talk about persistence length. Persistence length is more of a physics term, and it talks about how rigid polymers will act less rigid the longer and hotter they get.
Got it. So a good way to imagine this is kind of like with a rope. At short distances, it'll look pretty straight, but the longer the rope gets, the less it acts like a rigid beam, and the more it acts like, well, a rope.
Exactly. So when you put it all together, ARP23 doesn't just branch out for the sake of complexity. It's a way that cells can control actin mechanics, keeping filaments short enough that they stay stiff and functional rather than behaving like a floppy polymer.
And that mechanical control is what's going to let actin do its job in processes like cell movement, shape changes, and force generation.
From muscle contraction to cell migration, actin structure and regulation are what make its function possible.
Thank you for watching this week's episode of Physiology in Focus.
And be sure to tune in next time as we take a look into the mechanics behind cellular physiology.